Yeah, I'm really happy to be here as a speaker. I definitely wanted to go second because if you have to go on the third speaker spot, you have to make sure you pace yourself with the beer or else your entire talk ends up coming up as rubbish if I drink too much during the first act. So just a reminder, I arrived here back in August 2017 and then host Brandon Bozak and Raquel Martinez, who I'm happy to see are in the audience tonight, came to me and said that they had a speaker drop out last minute. Would I be interested in giving a talk? And so, only being here 2 weeks, I gave a talk, and I started with this slide back in Astronomy on Tap 36, where I had just come from grad school, where I talked about how I did grad school at UC Berkeley, and I had started a postdoc position with Professor Stella Offner at UMass Amherst. So that about a year before I came to UT Austin, I had packed up my entire life, along with Geo, my cat, into a car, and we had traveled across the country to work with Stella Offner. About a month after we arrived there, she informed us that she had actually gotten a faculty position here at UT. So 9 months later, we then packed up our car again and we came over to UT Austin, where we then were for about a year and a half, almost 2 years now. And I'm happy to say now, not this Friday, but next Friday, we'll be packing up our car again and more or less returning right back to where we started in the Bay Area, where St. Mary's College of California is located. Just to give you an idea, here is Berkeley, where I did grad school. St. Mary's is here in Moraga. About a 10-mile difference between where I started and where I ended up. So it really is full circle. Speaking of circles, binary systems. Now, they have a fancy sounding name, but the physics behind them actually is something that you are all very familiar with. If you understand the idea of an orbit, you understand the idea of a binary system. This goes all the way back to when Isaac Newton first came up with the idea, and he had a thought experiment of the cannonball being fired around the world. If I take a ball and I throw it out in front of me, gravity will pull the ball down towards the surface of the Earth, so the ball will hit the ground eventually. If I throw the ball even faster, it will go a little farther before hitting the ground of the Earth. And if you imagine if there was nothing in the way and I was able to throw it hard enough, it would be traveling so fast that by the time it started to fall towards the Earth itself would start to curve away from the ball. And so the idea of an orbit is really nothing more than something that is constantly falling towards the other object but constantly missing. That is the entire idea that was first proposed by Isaac Newton of what an orbit is. And if you understand that idea, where it's just the gravity of the two objects tugging on each other, in this case the cannonball is tugging on the Earth and the Earth is tugging on the cannonball, and they are constantly falling toward each other. Now, since the Earth is much more massive, we don't feel the Earth falling towards the cannonball. It looks like the cannonball is the thing that's doing all the motion. But if you use two objects that were more comparable in size, like Pluto and Charon, for example, they really are falling toward each other, and they orbit around this kind of invisible point, which is their center of mass. And so in all of these cases, and then if you have two stars, for example, that are about the same size, they are also orbiting each other around their common center of mass, and that is a binary system. It is also the same idea of an orbit. And so if you understand that, you really understand the basic idea of the talk. I could really just end the talk here and we could all go drink some beer. You have seen this idea with the moon going around the Earth, other moons going around other planets, or wannabe planets. You have seen this with planets going around stars. You have seen this with stars going around other stars. Here is Proxima Centauri A and B orbiting each other as a binary star system. When you have just the gravity of the objects pulling on each other, as long as they don't collide, that is a binary system. Now, as you zoom out, and notice that this is having over much different scales. You know, the distances here is 250,000 miles, where the distances here can be light years. It's a lesson we can learn from gravity. Gravity does not discriminate. It occurs at all length scales. And you understand it as long as it is just the gravity of the two objects pulling on each other. If you go up to larger scales, you might say, well, what about the central massive black hole and the sun? Is that a binary system? Not quite, Because it's not just the central massive black hole and the sun that are tugging on each other. The sun is also being tugged on by all the other stars and all the other stuff that's in the Milky Way, and there's actually more mass in that other stuff than there is in the central black hole. And when you include the dark matter in the Milky Way, that becomes even more the case. So while the sun orbits around the central massive black hole, it's not really a classical binary system. And then similarly, when you have galaxies orbiting around each other, like the Andromeda galaxy and the Milky Way galaxy, as they kind of orbit each other, admittedly, they actually are on a collision course. They don't operate like a classic binary because there's also a lot of dark matter, a lot of other things in the local group that is tugging on these galaxies. And questions we can ask, so just understanding the binary orbits are interesting, but we can ask other questions like how did these binaries come to be? When we look at all of these objects, we can ask how frequently you get binary systems. How frequent does this occur? Almost all the planets in the solar system, for example, have at least one moon. We now know that that probably all the stars in the Milky Way galaxy have at least one planet. And we know that about 50% of all the stars in the Milky Way have a binary companion. So is binarity ubiquitous? Is this something that is just a given? Or is it something that comes to be where we can take some time, and as a theorist, I want to then understand kind of the origins of binarity. Is this really ubiquitous, or is it something that comes to be in the universe? And since we're celebrating the moon, before I get to stars, I thought I would just very briefly talk about, our favorite binary system, the Earth and the Moon. We can ask again, if you were at the PBS event, I talked a little bit about this, we could ask about how did the moon form? Translating into the topic of this talk, how did the binary system of the Earth and the Moon come to be? How did this come to be a binary system? Astronomers have thought about this for a long time. One of the ideas, for example, was that they formed simultaneously. They just happened when the Earth formed, the Moon formed, and they just happened to be close to one another, and they formed a binary system. Another idea is the fission model, which was put forward actually by George Darwin, the son of Charles Darwin, the evolutionist, which was the fission model, that the Earth actually used to be spinning so rapidly that it pinched out a moon. Yes, the professor just made a poop joke. But the idea was that the Earth used to be bigger and it kind of squeezed out a moon. Another idea was that the moon formed elsewhere and it just drifted nearby and got captured by the Earth. Now, these are all very valid models, no matter how disgusting they sound. But as a scientist, they must be supported by observations. And the moon is great because we actually have been there. We have data that we can use to see, do any of these models make more sense than the other? And one of the things we find that we know about the moon is the composition of the moon is very similar to the surface of the Earth. The composition that is on the surface of the Earth, so not iron, but carbon, is very similar to the composition of the entire moon, where the interior of the Earth has a lot of iron. The moon seems very iron deficient. So if they formed simultaneously, that doesn't make sense, because if they both formed simultaneously from the same stuff, you would think they both would have a similar composition, so that can rule that one out. The squeeze model could explain this, but that doesn't explain another data point, which is the fact that the moon is tilted relative to the Earth. If it was squeezed out of the Earth, you would expect it to be on the same orbital plane as the Earth's spin. And there, in that case, we would actually get total solar eclipses every month, because it would be in the same plane as the sun. But that doesn't seem to happen. And then if it was just randomly captured, then we would think there would actually be more of a difference in the composition than we actually see. The fact there's enough similarity suggests that something is going on, which led to the idea of the coalescence model, where the Earth used to be much bigger, and a Mars-like size object actually impacted the Earth. So it's showing you kind of the exterior and then the iron center of both objects. And when the collision occurred, it's kind of hard to see, but the stuff that is thrown out, notice it is not the iron in the center, but it's actually all the outer parts of the Earth that got thrown out into space. So, and from that, we believe that debris from the collision impact formed the moon. This supports the observational evidence. You always have to tie, as a theorist, I always have to tie it back to observations. I always have to tie it back to data. So this is just one example of our favorite binary system. Now, I want to do the same with stars. we can't expect to do this with as much detail as, say, we did with the moon, because we can't really go to stars other than the sun, and even then that's quite difficult. But I want to, in general, kind of understand how binarity came to be. And the observations say, again, that when we look around the Milky Way, we see that no matter where we look, about 50% of the stars are in binaries. So no matter what sort of environment they're in, about 50% of stars are in binaries, which suggests actually that we have to go farther back in time. That suggests that it's not a product of just letting them kind of roam about the Milky Way and eventually these binaries form. The fact that no matter where we look, no matter what the ages of the stars are, we see more or less the same thing, suggests that this binarity is probably coming about when the stars formed. This is probably something that is set during the star formation process. So instead of looking throughout the entire Milky Way, we can zoom in on the places where stars form. And the stars form in spiral galaxies in the spiral arms. Spiral arms really are just cosmic traffic jams, where lots of gas and dust and other stuff kind of just collect into these spiral arm patterns that, like we see in the Milky Way and in other galaxies. And that allows a lot of stuff to be in a relatively small amount of space. And that's really what you want to form stars. You want to get a lot of stuff in a small enough space so that gravity can take over. Gravity, again, does not discriminate. It sees all the stuff around in the spiral arms. It starts to pull things together and pulls things in, and you eventually get stars that form in these spiral arms. So we see evidence when we look at the spiral arms of our galaxy and other galaxies, evidence that there are new stars forming as we speak. Probably the most famous example is the Orion Nebula. It's my favorite because it's one of the few constellations I know. If you ever want to stump an astronomer, ask them to point out constellations. They are not really important to us. So I can point out the Orion Nebula because I can easily find the belt, and you can see the Orion Nebula, or you can see the Orion belt with your naked eye, and you can also see with your naked eye the Orion Nebula. And this is just invisible light. So this is one of the most studied places in the sky where tons of stars are forming as we speak. If we look in the infrared, which is better at tracing the gas and dust, the cold gas and dust in space, we see that the Orion Nebula, which is in a spiral arm of the Milky Way, is actually part of a larger complex of filamentary gaseous this large network of gas that exists, and this is called the Orion complex, that extends tens to maybe hundreds of light years in distance along the spiral arms, where we see evidence that stars are forming in multiple places. Here in the Orion Nebula, the trapezium is one example of a famous set of stars that have very recently formed. They are the 4 very bright stars in the center of the Orion Nebula. One of them actually is a binary. There are 4 stars, and 2 of them are a bound binary star system. There's some star formation that's going up on here. So there's lots of star formation that's going on in this large complex of clouds inside the Orion complex. And also notice that these are not nice calm regions. These are nice, these are not spherical regions of gas. These are nice, not puffy, nice clouds. These are actually very chaotic, churning, turbulent clouds of gas where there's a lot of internal motions, but then gravity is pulling everything together, and within that, you form stars. And so we can ask observationally, what do we see when we look at places like that? And when we look at where stars are forming, we actually see tons of binaries. We see lots of binaries. More binaries actually than we see when we just generally look at any random place in the Milky Way, which does suggest that binarity, whether you form binary stars or not, does occur when stars are forming. That binary stars form when the stars form themselves, and then hopefully most of them, we want to try and understand that, persist after the star formation process and then just continue their lives as binary star systems. But the tricky thing with observations is you really only get a snapshot when you do an observation of a star forming region. And star formation takes place over millions to tens of millions of years. And while I might now be power hungry as a professor, I would be fired immediately if I took on a student and said, for your PhD thesis, you have to wait 10 million years in order to study this region of the sky, in order to study one star-forming region, because that's how long it would take if we actually wanted to see it happen in space. This is where simulations can help. This is where we can do simulations. It's much easier for me to simulate 10 million years on a computer than it is for me to wait around 10 million years taking pictures of the sky. But the sky provides data that I then have to compare my simulations to. I have to make sure my simulations I can use my simulations to understand what we're seeing in the sky. So for example, what we see is when we look at the separations in star-forming regions, we're going to focus just on this one plot. There's lots of questions we could ask. I'm focusing here on the separations of binary, so the distance between the two stars in the binary system. And what we notice is that it appears to be bimodal. There are two peaks. There's a peak here, which is about the size of the solar system, so about 100 times the distance between the Earth and the Sun. So stars form about 100 times more farther away than the Earth and the Sun form away. That's actually very close on a galactic scale. They are very close to one another. And then there's the peak out here, which is about 10% or so of a light year, where it seems like there are also a lot of other binary stars that are forming with much larger distances. So you have these wide orbit binaries, and then you have these very tight binaries. And so a question you could ask is, did this bimodal peak form like this, or does it evolve into being something like this? For example, did these stars that have separations that are about the size of the solar system, did they form as a binary with separations the size of the solar system, or did they form as something else and become a binary that's the size of the solar system? And then similarly, you can ask the same question for these guys that are farther out. And so currently, the leading idea is that these are actually possibly forming in situ, that these are a result of two different formation processes, that there are two ways to form binary systems. So on the small scale, we think this is an example of what we call disk fragmentation. So that you have one binary star that forms, and as it forms, it creates a giant accretion disk around it. The leftovers of this accretion disk actually is what forms the planets. But you can see the disk kind of forming, and if that disk becomes big enough, the gravity within that disk can actually cause the disk to collapse and form a secondary star within the disk. You'll see it in a little bit. So there's a black dot here, and then there's going to be another one that kind of pops in after a little bit. There we go. You see it now. So within the disk around one star, another star forms. And that can give you a binary star system with separations that are about the size of the solar system. Then the idea with these stars is that these stars form through what's called turbulent fragmentation, where think back to the Orion Nebula. That wasn't a nice calm cloud. There was a lot of chaotic motion going on, where there's a lot of randomness going on, just kind of random fragmentation as gravity pulls gas into one another. You see you form a star here, and then you formed a star over here. And they have nothing to do with one another, but they form close enough that they can form a binary system that then they remain gravitationally bound. And so the idea is that, is this peak a result of something that's happening? You know, are these two different formation processes? And that's one of the questions we want to answer. Again, we want to be supportive. We want to support our ideas with data and our theory with data. So another piece of data that's interesting is that these stars, when we see stars that are in these large separations, they tend to be very young compared to the disk stars, where they tend on average to be a little bit older. So so whatever theory I come up with, hopefully it also gives an answer to why that's the case as well. And so, to do simulations to understand this, I call up my friends up the street at the Texas Advanced Computing Center and ask for time on a supercomputer, just like how the observers ask for time on telescopes. I ask for time on supercomputers in order to run simulations to understand how binary stars come to be. So what we did is we ran 3 large simulations of 3 different clouds of gas. So we kind of created 3 different clouds like Orion, for example. And each one and we also wanted to ask the question, does the magnetic field in these clouds, so these clouds that we observe in the Milky Way tend to be very magnetized, does the magnetic field make a difference in terms of what kind of binaries form? You know, maybe it's the magnetic field. Maybe that's the piece of physics we're trying to test here. Maybe it's the magnetic field that is making these binaries. So first thing you have to do is you have to make the cloud. So the first part of the simulation is to kind of take 3 simulations and with a figurative spoon kind of shake it up so that you get kind of chaotic looking cloud, you know, things that look kind of very similar to what you see when you look in star forming regions in the Milky Way. And you can already notice that the magnetic field is making a difference here. The darker the contrast between the colors, the more difference there is in the density of the gas. There's lots of contrast here compared to not a lot of contrast here. So you're already seeing that magnetic fields are kind of changing, already setting up for the answer to be different. Because you're doing 3 different clouds now, and we want to see which one of these, if any, make the right kind of binaries, and if they do make the right kind of binaries, can we understand what's going on? So then after we make the clouds, we turn gravity on, and we see what happens. So you'll notice as gravity does its thing, things will start to become more condensed. Red regions will become redder. That's the gas getting denser. And you see stars will start to pop into the picture. And this is for simulation 1, simulation 2, simulation 3. Let's go back and do it again. And the number of stars that's forming, you can see up here, is one of the things you see that's immediately very different between the 3 simulations. Strong magnetic fields are only forming a couple, a half dozen of stars, where the weak magnetic field is allowing star formation to occur incredibly rapidly. Lots of stars are forming in the strong magnetic field case compared to the weak magnetic field case. And so it's interesting because you could think then, well, maybe that gives more potential for there to be binaries in this case compared to this case, if there are more stars. But also notice that most of the stars are forming in the same exact place. It's a very crowded environment. Some of them even get thrown out because there are so many stars in that crowded environment that they are interacting with one another, which doesn't seem like a nice way to form binary stars, in my opinion. So what do we find? One example of something we find is that when we look at the fraction of stars that are in binaries, we match the observations, so what we see in the Milky Way, much better if you have strong magnetic fields. The strong magnetic field actually helps you keep the binaries around. Because in the strong magnetic field case, you can see there's a binary, you can kind of see 2 stars right there, kind of on top of one another. It forms a binary, but since no other stars really form around it, that binary is able to persist for long amounts of time. Compared to the weak field, where there are a lot of binaries in this case, but they are all so clustered and crowded with one another that they immediately get disrupted with one another. I have an example that shows this. So the magnetic field is helping retain the binaries, and with a stronger magnetic field, ones that actually match what we see in clouds in the Milky Way, it seems to be what is setting what fraction becomes binaries or not. And you're getting about 50%, which is about what we want at the end of the day. Where in the weak magnetic field case, the numbers are much lower. Something like 25% are in binaries. So here's an example of turbulent fragmentation. You have a couple of binary stars. You have a triple star system here and a binary here. I let them do their thing. They kind of dance around one another. All seems calm and peaceful. But then, oh hey there. Another guy comes in. Large gravitating disk. It disrupts everything that's going on there. And notice at the end of the day, everything kind of just goes to shit. So while the binaries were forming, they didn't persist because the gravitational interactions of other stars actually screwed things up. And here's just kind of an example of the start and the end. There were a couple binaries. In this case, at the end of the day, only 2 of these stars were actually in binaries. Most of them were thrown out. So, and here's the same exact thing, kind of from a different point of view, where you see, guys get close to one another, and one wins and one does not. And then those stars, you can actually see the stars being thrown out of their disk and away from one another. So that's one of the questions we had to ask. Does magnetic fields seem to matter? The answer seems to be yes. Magnetic fields do seem to help regulate binary star formation. We also wanted to understand those 2 peaks, where those 2 peaks came from. And when we look, and so don't mind the colors, just these are all kind of binaries and multiple star systems. When we look at the distances between the stars, we notice they all evolve over time. They start at very large distances at earlier times, and then as time progresses, all binaries have a tendency to shrink to shorter distances in between one another. So they start big and they end small. Let me just put back on top where those 2 peaks were. Notice everything is kind of starting where the first peak was, and it's ending where the second peak was. And that's fascinating. to me. Because if they start very young here, and remember this peak had mostly young stars, and they end here after time has progressed, so they have aged a little bit by now. So it seems like this simulation is both getting where both of those peaks might be coming from, as well as why one of them is young and one of them is old. Of course, I could end it there and just claim victory, but I really need to be able to justify. You could ask yourself, well, why are these binaries changing? Why are they getting smaller? Here's just an example where these two stars start with distances that are about 1,000 times the distance between the sun and the Earth. But notice at the end, they are very tight. A third guy comes in and plays. And these kind of end up very small orbits compared to where they started with distances that are closer to 2,000. So they start big, they end small. Something is going on here. And here's kind of the start separation and the kind of end separation. They end very, very tight, but they start very large. And the idea here is that these stars are in this giant gas cloud. They are interacting with the gas as they roam around this gas cloud. We can't ignore the gas. And it is the gas that is causing these orbits to shrink like this. So this is a concept called dynamical friction. So here's my cartoon image of this. So you have a star that is moving to the left, and so relatively all the gas is moving to the right. If it starts off with the gas more or less uniform, the gas is tugging on the star kind of equally in every direction. So there's no net force on the star. It's being tugged in the same way in every direction. But as the star moves this way, it is still trying to pull the stuff towards it. Some of that stuff will fall onto the star. Then the star accretes, it gets bigger. Some of that stuff will fall towards the star but miss, because by the time it got to the star had moved out of the way. So you kind of get something that looks like this. So there was stuff that fell onto the star, but stuff that tried to fall onto the star but missed because the star moved. Now the symmetry is broken. There's more stuff here than there is right here. There's more of a tug behind the star than there is in front of the star. It's like if you had a rope wrapped around your waist and you were running and you had a friend that was tugging back on the rope. That is going to slow you down. It's going to take more energy to overcome this. This is the idea behind dynamical friction. And so if we put this if I model this and try to see if my simulations agree, I was happy to find that if I took my simulation data where I took a binary that then kind of started very big and shrunk to very small, that's the black curve. And then this very simple model that I had just explained to you, if I model that, I get the red curve. No, I don't believe you. A standing ovation would have been appropriate. But this is nice because this suggests that we're on the right track. We're actually understanding the relevant physics that's going on here. That the binaries that are forming, let me skip ahead to this. Binaries are forming at both small and large distances, but this distribution is not just from things forming from disks and things forming from turbulent fragmentation, but it is actually a combination of guys out here that form and then they migrate or they evolve to smaller distances so that these two peaks can be explained by a complex physics of not only disks and turbulent fragmentation, but as well as dynamical evolution and capture. And then the magnetic fields obviously help you get the right answer. Now there's a lot here we can keep thinking about. This was only a couple questions we could ask about binary stars. I really just told you, one example of kind of how we can understand binary star systems. But luckily, I still have a lot of time, in my new fancy position to keep thinking about this. So thank you.
All right. Thank you very much, Aaron. Let's do time for a few questions. He's grabbing his beer. Okay, time for a few questions. How about over here?
Should we expect the binary star system to persist for the entire life cycle of the stars, so that maybe at some point every binary star system is like two white dwarfs?
So the question was, should we expect binary star systems to persist throughout their entire lifetime? And I guess you're thinking even beyond their regular lifetime when they become things like white dwarfs and neutron stars, stuff like that. Possibly, it depends. So the interesting thing is, like, when you get to galaxies, when you just look at the Milky Way, stars don't really interact with one another. You know, they are very small on the galactic scale. So if you're in a binary, you know, by the time you get out into the Milky Way and you're done with the star formation process, chances are that you probably won't get disrupted at any time during your life, and you will remain a binary through most of your life. Now, whether or not that continues to pass the, you know, once you retire as a star and start becoming something like a white dwarf or a red giant or a neutron star, that will depend a lot more on kind of what the end state is for the stars that are in that system. You know, two stars that become red giants and then white dwarfs have a much higher chance of staying gravitationally bound to one another compared to if one of the stars were to go supernova. You know, that's a very energetic explosion that might blow the other guy away. But we know that these exist because we think type 1a supernova, for example, is when you have a star and a white dwarf and the star feeds the white dwarf until it explodes. So we know these sorts of objects do exist. Yes.
All right, let's see. Let's try to get maybe from the balcony way in the back there, up high.
Great question. So the question is, yes, there seems to be a bimodal distribution, but if what I was saying, if some of these guys that start out here then evolve to become these guys, why is it not more evenly spread out? Is that more or less what you're asking? And you're right, the process that these guys can become smaller separations can be very quick. Quick on astronomical scales, which is like 100 kiloyears, 100,000 years or so, which is really nothing in terms of, you know, the astronomical time scale. So this can happen very quickly, yes. You know, kind of a related question is then kind of where do these guys go at the end of the day? Do they all become small guys or do some of them hang around? Because when we look in the Milky Way as a whole, we do not see binaries, a lot of binaries at these distances. Actually, I didn't mention this, but this dashed line, this dashed curve here, is actually what we generally see in the Milky Way, not regions where stars are forming, which is where you see the bimodal distribution. So that's another paper. That's a question of kind of how you go from star-forming regions to the binaries that you see generally in the Milky Way. Because then maybe these guys just kind of spread out and become this. Maybe it's something else. That's another question.
All right. Yeah, let's do one more question. Let's see. How about front row, sir?
Yes, hi. I'm curious about the process when you go to do these simulations on these supercomputers. Are you drawing to, I assume you're generating some algorithms. Are you drawing from classical fluid dynamics, like with atmosphere and water? Are the same dynamics occurring in these big gaseous clouds?
Yeah, so the question was kind of on the supercomputing methods. So these are large magnetic hydrodynamic simulations. So yes, we're using classical fluid dynamics, but what is convenient in space, fluid dynamics becomes much simpler in space than it does here on Earth. Like you were talking about water, for example. You know, to model water on the Earth, you have to take into account surface tensions and all sorts of inner molecular forces because all the water molecules are very tightly compact to one another to make a liquid versus a gas. In space, everything's a gas. So it's just more or less just a bunch of dots flying around. And in my simulations, actually, I don't even really necessarily worry that much about composition. I just treat it as a general fluid and see what happens. And then where things get really dense, I replace it with stars. But yeah, there are some space cadets here that think a lot about astrochemistry, so you can hit them up if you want to think about chemistry in space. They've thought much more about it than I have.
All right, thank you. Let's thank our speaker one more time.